Okay. All right, can everybody hear me? All right, last talk. So I'm Ryan Brennan. I'm a graduate student at Rutgers University. I work with Rachel Somerville, who's a collaborator on this work, obviously, as well as Ina Choi, who's a postdoc at Rutgers. And this is, ongoing work. This is work that we started fairly recently. I do want to plug a paper that recently went up on arXiv in collaboration with Candles and several people in this room that were in the process of editing and resubmitting. So check that out. I decided not to talk about the thing that had actual concrete results yet, because that's usually a good idea, but here we are. So we're going to talk about simulating galactic outflows with and without active galactic nuclei. And so we have 32 sets of 30 zoom-ins in the gadget SPH code. And in half of those, we have a seed black hole, and the other half we don't. And so here the difference is illustrated pretty strikingly just on this title slide. These nice outflows in the AGN run, and you don't see that in the no AGN run. So quick outline. I'll give some very brief background. We've heard a lot about this stuff already. I'll talk about our model, and then results, which, again, may be a charitable word, but I'm open to ideas. So we think that AGN feedback is important, at least for the evolution of some galaxies, and many people have pointed to the apparent coevolution of galaxies and their central supermassive black holes to help explain this bimodality we see in the galaxy population. So on the left, there's the M-sigma relation, and on the right, we have this bimodality here shown in the color magnitude plane. No, whatever. And we see that bimodality in structure. We see it in star formation rate. And so when we talk about this AGN feedback, theoretically, it usually comes in two varieties that we've heard about so far today. One is this quasar mode feedback. I think we even saw this image earlier today. And that's, this powerful ejective feedback that moves gas out of a galaxy is associated with a higher accretion rate for the black hole. And then we have this radio mode feedback that we just heard a lot about, maintenance mode. And I'm going to focus on this quasar feedback, which is, invoked to correspond to these large-scale outflows that we see in the universe. And we see these manifested in a few different ways. An example is broad absorption line observations, where we see material between us and a quasar being moved very quickly, and we see that in these broad absorption lines. And that gives you a sense of how fast gas might be moving, but it doesn't really give you much information about the spatial scale. Now we have integral field spectroscopy, and we're getting some really cool results looking at outflows, such as this, where we have in each of these 9 spatial bins, you have the spectra, so now you have spatial information as well. But we're still, handicapped because we're seeing this at, in one snapshot of time. We're stuck seeing it from one angle. So why do we study models? Because we have this God's eye view where we can see, anything we want to about this outflow. And we can turn physical processes on and off and see, their explicit effects. And so what we've done here is we've run, like I said, 30 zooms, the same initial conditions. And in half of those, we have AGN feedback, and the other half we don't. And so that's what we're going to do here. So what is our model? It's a modified version of the Gadget 3 SPH code. We have lots of stuff. We got feedback from supernova, massive stars, metal enrichment, metal line cooling. And then we have this, again, we have this AGN feedback prescription that is meant to drive these very strong winds. So it's mechanical radiation driven. We drive a fast wind. We have a subgrid driving of a fast wind right around the black hole, and then those gas particles impart momentum to their neighbors, and we drive this strong outflow in this way. We have these two series. The final central galaxies have a stellar mass of about 10 to the 11, 10 to the 12. And this model is shown really successful in being able to produce the realistic massive early type galaxies, which is what it was designed to do. And so really for the rest of the talk, I'm going to walk through some examples of these 30 cases that I have. and see how this AGN feedback is affecting these galaxies. So here we have gas particles color-coded by their temperature. On the left we have the case with AGN, and on the right we have without. And so the first thing you see with this one is that by the end of the run, it's just going to keep looping, is that the results don't look that different. We end up with a lot of swirling hot gas in both cases. We see these satellites swirling around. We actually end up seeing more satellites. There's more evidence of satellites in the AGN run towards the end because there is actually gas being moved out. It's not, you can see these bursts. And so the gas is more diffuse. And so the satellites don't get stripped quite as quickly in the AGN run when they come in as they do in the no AGN run. So just a visualization. We've also gone through and we've started to track these gas particles as the main bout of AGN feedback kind of explodes. And so we have on the top left and bottom right kind of the same movies we just, top left and bottom left kind of the same movies we just saw. And now on the top right and bottom right, we have cumulative mass in these 4 bins versus time. And so these 4 bins are accreted gas, which is gas that's passing into a 20 kiloparsec sphere around the black hole. Outflowing is passing out of that same sphere. Ejected is an outflowing gas particle that later has a kinetic energy greater than its gravitational potential energy. And then expelled finally is an ejected gas particle that later passes outside of the virial radius. And so the first thing that jumps out, well, one of the first things that jumps out is that we have far more, a lot more mass being accreted onto this, center of this large region in the no AGN run than in the AGN run. And we have far more being expelled, leaving the, the virial radius of the halo in the AGN run. We actually see more in the outflowing and ejected bins in the no AGN run because there's more material to move out, but almost none of that is, very little of that is making it all the way out to the virial radius. And that's a result of stellar feedback and in some cases satellites coming in and then shooting back out. But we also have that in the AGN run case. So here's another example. So this one is a little more spectacular because we have satellites that are also undergoing AGN feedback as they come in. And so this one is a little more chaotic. And what's nice is in the without AGN case, we see in the absence of that, we have this cool gas disk that starts to form instead. And then if I'll let that go one more time.
When is the quasar turning on?
So in, like at what time? So each of these, it comes at different times. In this specific case, the real big explosions start here, like redshift of 1, a little before redshift of 1. But it happens at different times for the different zooms that we have. So if we look at the same kind of analysis here for now the for this zoom in, we have here almost all of the material that's either outflowing or ejected in the AGN run makes it to the virial radius because this is a more explosive feedback than we saw in the previous case. And in the without AGN run, much less even makes it out of that inner 20 kiloparsecs, which maybe intuitively makes sense because enough is left to actually cool and condense down into this gas disk. 501, this one is pretty cool. This one basically blows an entire filament apart. So, and we see this guy turn around. I love that guy on the right that just comes in and then zips back out the other side. Meanwhile, in the no AGN case, again, we see this gas disk forming. So, this is a case where we have basically preventative feedback where it's preventing anything from really even coming onto this galaxy from fairly early on. Rachel really liked this one. All right, I have one more minute. Okay, and I just wanted to remind you, because I need to remind myself, there are still stars coming in towards the center in this run. It's just that the gas gets blown out by the outflow as it's making its way in. And then finally one more that's kind of similar to this one. Oh, well, I still have this as well, but I'm running out of time. So again, it's kind of a similar story. We get a ton of stuff get blown out in the AGN run and not so much here. in the no AGN run. 948 I just think is really pretty, and it was my title slide because you can almost hear the explosion as it starts up. There it is. I love that. Okay, but anyway, so this has all been. I really like looking at these movies, and again, you see everything get blown out at once. But what do we want to do with this? So, this was kind of our first step, just quantifying how much gas is being moved around due to this AGN feedback, as opposed to how it would be in the absence of that AGN feedback. But our goal now is to try and link, properties of these outflows to, the properties of the galaxies. And then eventually our ultimate goal is to translate these outflows to observables, make like mock IFU observations, and look for correlations between the observed wind properties and galaxy properties and try to interface with observers a bit more with our knowledge that we have of this whole, outflow on a global scale. And yeah, that's it. Thank you.
So Chair's prerogative. Can you remind me, maybe I just missed it, what halo mass scale this galaxy was again?
So the halo masses are in the range of, about 10 to the 12, 10 to the 14, something like that.
Okay.
Yeah, like in that range.
Another question.
I must have missed it. Maybe I did. Did you explain why your AGN feedback is so remarkably efficient when other people have not had such success?
So a lot of the AGN feedback you see is thermal, where they dump thermal energy into the gas particles. And we found that we couldn't recreate, Ina Choi found she couldn't recreate realistic elliptical galaxies with this thermal feedback prescription. So we have this momentum-driven feedback prescription. So we launch a very fast wind right around the black hole of 10,000 kilometers per second. That's like our subgrid recipe. And then each of those gas particles imparts momentum to its nearest neighbors, and that's,
Do you think you'll be able to reproduce, say, X-ray halos in some of these powerful?
I hope.
Nice.
I mean, it looks like you. I mean, just again, like this is all kind of qualitative, but I feel like it looks like you could. I mean, we need to. So we have. Yeah, I don't know. We need to think more about what exactly we want to compare observationally with.
I'll give you a tougher challenge.
Oh, jeez.
One of the surprises observationally is that we found quasars, when they're shining, are surrounded by cool gas, 10 to the 4 Kelvin, a tremendous amount. It's hard for me to parse from your movies, but
yeah.
I'm seeing a lot of 10 to the 5, 6.
Yeah, there's a lot of hot gas. Yeah, I don't know. There is some cool gas. I mean, it's hard to, so like these movies, we wanted to see kind of all of the substructure falling in. If you look closer, there is some cool gas. It's not a huge amount, though. You need a huge amount. Yeah, we don't have a huge amount. I don't know. Yeah.
I'd like to point out an interesting feature concerning AGN feedback, which is a little problematic. And this is in star-forming galaxies. You don't want AGN feedback to be too effective in star-forming galaxies. For example, at redshift 2, we have this problem to reproduce the high specific star formation rate, which is a factor of 2 or 3 above any model. And with AGN feedback not allowing recycling, we have a problem. We must have recycling at redshift 2 or 3 to try to understand the very high specific star formation rate. So yes, it should be very effective in quenching once you are becoming a passive galaxies, but we should be careful not to make it too effective when you're star forming.
Yeah, I mean, we're not saying that this is, like cosmologically representative. We wanted to model very strong outflows that quench galaxies effectively. So, this is one class of object that we were kind of wanted to focus on.
All right, and that's very quick.
Were all your remnants elliptical galaxies, or were some of them like S0s or lenticulars?
Yeah, all of the AGN remnants are, like massive elliptical galaxies.
All right, let's thank our speaker again.